All right, guys, here we go. First lesson for chapter 1. We do jump over 1.1 and we start off in 1.2. This should be some familiar stuff for you with domain and range and functions and mapping diagrams. All these are things that you would have seen in Algebra 2. So a little refresher on some of these guys. As far as domain and range go, we always know that domain sort of represents the x values within a function, and the range represents the y values. The other way that we look at that is the domain. If we have a function like, let's just say our function is f of x equals 2x plus 1, right? The numbers that we put in for x are the domain, that's the input, and the results, the y values that come out of those, are the range, right, or the output. There is some good information on page 78. I'll show you that real quick here. So you can always, So you can always jump over to your online book. Remember, I have directions for this in the website in Canvas for getting into My Math Lab, and that's where you'll find the e-text, which is this, which is your book. So I'm looking on page 78 right now. So they got just that basic same kind of information here as far as domain and range and what qualifies as a function. So one of the things that we want to keep in mind with this, and this is always that kind of machine diagram that we discuss when we talk about domain and range and what qualifies as a function or not a function. So it's like whatever you put into the machine, your input, that's your domain. That's what goes in. That's what we call the independent variable, because it's what we choose. We choose to put what we want into the machine, so it's independent of anything else. And as we put the domain values into the machine or into the function, what comes out of it are the y values, and that's what we call the dependent variables, or the output, or the range. All those things mean the same thing. So what qualifies as a function or not a function? When you put an item into a machine, it should only produce one output for each input. We call that a one-to-one function, right? So if I put one item in, I get one result for each item. So if it's a one-to-one function, that would be a function. If I can put one item in to my machine and it produces two different results, then it's no longer a function. So here's in the mapping diagram, here's an example of what would be a function and what's not a function. So you can see on this that this is a one-to-one function, or actually I should say this is a one or many-to-one function. Anytime you have more than one input producing the same result, we call that a many-to-one function. But it's still a function because as I put in each input, I still only produce one result for each input, right? It's the case where you take one input and it produces more than one result. Like you can see right here, this x produces that result, this x produces that result. So anytime you have an input that produces many different results, it's no longer a function. So we would call this a one-to-many function. So that's kind of the only time it's not a function. So if it's one-to-one or many-to-one, that's okay. But anytime you have a one-to-many scenario, that's when it's no longer okay or not a function. So some good info on there for you, page 78. Let me jump back to the notes here so you can fill in those things with whatever you want to take away from that little discussion. When you have a graph, and this is something you guys learned a while back, the whole vertical line test tells you whether or not something is a function. So if I can draw a vertical line through a graph and hit that graph in more than one location, that becomes the one-to-many case where it's no longer a function. It fails the vertical line test. If I can draw a vertical line anywhere on the graph and only hit it once at a time, then it passes the test and it is a function. So let's jump over to some examples of domain and range. So if you did print out these notes, I'm looking at this spot right here as we turn the page on those. So here's just some examples if I'm given functions like this and we're asked to come up with a domain on any of those scenarios. All right, so if you take a look at these guys, so remember, domain has to do with the values that we put in for x. So really the question that you're asking on this is, what values am I allowed to put in for x? When you get into square roots, you guys know that for an even root, you cannot take the square root of a negative number. So whatever is under a radical, in this case the x plus 4 is under the radical, so whatever that is has to be greater than or equal to 0. Right? Because we can't take a negative under an even root. So as I look at this, if I were to solve that little inequality by subtracting over the 4, then we know that the x's that we are allowed to plug into that function must be greater than or equal to negative 4. One of the things that we're going to deal a lot with in this course is a graphing calculator. So I want to sort of go back and forth here. So if I were to graph that same function, so right here, if I go to y equals, and I just put in that same function that we see right here, right? And then I'm going to go ahead and hit graph. So take a look at the square root graph. You can see that it's just a square root graph that was shifted left 4 units. And so as I look at this, so you can see the domain. If you look at the x-axis here, right, you can see that that graph goes from negative 4 to the right, right? And that's where that domain comes from. It's all the x's greater than or equal to negative 4. So whenever you're looking at these guys, there's really two main things that we consider with even roots and with fractions like this is remember that whatever's under an even root has to be greater than or equal to 0. Whatever is on bottom of a fraction cannot equal 0 because we cannot have a 0 on bottom of a fraction. So for part B here, you have two things going on. For one, according to what I see on top, I know that x has to be greater than or equal to 0. And what I see on bottom is that x cannot equal 3, right? Because that's an issue. I can't have that 0 denominator. So what I need to do is come up with one statement that satisfies both of these scenarios. It's got to be greater than or equal to 0 as well as not equaling 3. And so really the best way that we're going to do this, and the habit I want you guys to get into, is using our interval notation, not inequalities like this. Right? It's going to be best if we use our interval notation. So what we could have done for this first one here, for x is greater than or equal to negative 4, would have looked something like this. And we dealt with this in all the prerequisite videos. So from negative 4 to infinity. All right, so that would have been the better way to write that answer. So what about something like this? So got to be greater than or equal to 0. So we are heading towards infinity, but I have to take this into account. We have to skip over the 3. So we're going to go all the way up to 3, non-inclusive, and we're going to union that with 3 to infinity, also non-inclusive, right? So this means we're starting at 0, going all the way up to 3, but not including the 3. You can see we sort of jump over it here. And then we're going all the way up to infinity. So this would be the best way to identify a domain for something like this. As far as x squared goes, so this, they're now limiting it to a geometric figure though. So it's the area of a square with side lengths of x. So if I just had this function right here, if it was just saying x squared, well, you guys know that that would represent a parabola that just looks like this. Right? And so if it was just a general statement for x squared, we would say that represents all real numbers because this guy goes left and right forever. Right? And so we would have said that it goes from negative infinity to positive infinity in a case like that. But this extra information limits that idea. Right? And so if this is going to represent the area of a square with side lengths of x, well, what is that? How does that affect the function that I'm looking at right here? Well, obviously we cannot have the area of a square or the side length of an x representing 0 or a negative, or it would not exist. So it's got to represent some positive value. So we have to sort of alter this domain to make sense with this problem, which would mean that we have to have something greater than 0. So it's anything from 0 to infinity we would have to use in order to make sense for this information that we're seeing right here. So we do have to take that into account when it represents something more than just a general function. So I had whited this out so you could have filled in that information here, but I kind of wanted you to see it at the same time we were discussing it. So I wanted to show you real quick, if you would have graphed all three of those, here's what those graphs would have looked like. Here's the second one that we did. We talked about that it was greater than 0 all the way up to 3, but it does not. Here's what we call our vertical asymptote running right through 3, right? That's like a boundary line. It's an imaginary boundary line that our graph is not allowed to touch, right? So it forever gets closer to 3, but once it hits that 3, it skips over and goes to the right of 3, and now this guy goes on forever. So remember that domain is always looked at from left to right because it is your x's. The range is what we look at vertically, right? This is my range, would be something like this. So anyway, domain on that we already talked about. Here's the graph of the third one that we did, and again, the calculator, like it says here, wouldn't know what x represents, so we have to sort of fill in the blanks on that and say, I'm really only looking at, I'll give you my own version, I'm really only looking at the graph that goes like this, right, as far as the domain that we're talking about. Okay, moving on. So these were just some more examples. So this is sort of the point where you can pause and practice some of these on your own, and then listen to my video, or you can skip over if you don't feel like you need it. So let me go ahead and discuss these, and you can kind of deal with this portion on your own for however you feel like you're doing on domain so far. So again, what we talked about with a domain like this one for number 2 is that whatever is under my, I'm going to sort of see if I can fill that one up here. Whatever is under my radical must be positive or 0. So that's how I would deal with the radical. I also know that x cannot equal -2 because of the denominator. Can't have a 0 down there. So I need to come up with one expression that would satisfy both of those pieces of information. So this one, and we could divide both sides by 2, and it really just tells us that x is greater than or equal to 0. So it's real similar to the one we did earlier. I know that I can go from 0, sorry, I have to take this guy into account. So if my domain says that x has to be greater than or equal to 0, that already takes care of this piece of information, right? We already know that x cannot equal -2 based on this statement right here. So really, just by putting my domain as 0 to infinity, this statement already takes care of this piece of information, so I can leave my answer just with that look right there, because that already covers that it cannot equal -2. So that would have been good enough for that one. So let me jump over to 3. So for s representing the perimeter of a square with side length of s. So again, if my s represents the side of a square, like we talked about with the other one, you cannot have a 0 or a negative when it represents a length, right? Or it wouldn't exist. So we just simply know that s must be something that's greater than or equal to 0, which is just going to look like this domain right here, from 0 to infinity. Jump over to 5. Again, anytime I'm looking at an even root, like a square root, I know that whatever is under there cannot be negative. So that's how I would write it, as an inequality. If I solve that inequality, so I'm going to add 1 and divide by 2, and I get this statement right here. So now I'm going to change this into interval notation and say that we are going to go from 1/2 all the way up to infinity for our domain. So do remember that because of the equal sign, that's why we put the bracket. It means that we are including the 1/2. Infinity isn't really a number you can land on, so we always use a parenthesis when dealing with infinity. And then this guy over here, real similar to that kind of information. You have 2 issues on bottom. We know that that x, because it's under the square root, cannot be negative. Because it's on bottom of a fraction, it can also not equal 0. So I just need one idea that takes care of both of those pieces of information. So in this case, if we just said the domain goes from 0 to infinity, right, we are not including the 0 because of that statement right there. And so now this domain satisfies both of those concepts. So let me flip over. Give you guys these. So I'm going to be flipping around a little bit on this, but I wanted you to get just a couple more concepts here as we sort of close out the first part of 1.2. So like I said earlier, when it comes to range, as you look at the graph, it's like, what is your graph doing vertically? What is it doing up and down versus the range, which goes left and right? There is an algebraic approach to finding the range because the range can be really tough to find without looking at the graph, but that's something we're going to discuss in later this chapter. So for now, I just want you to get used to looking at range graphically. So let me do that with you really quick by looking at these three graphs. So as far as the range on this, I'm just looking at what is my graph doing from bottom to top, right? I'm only looking this direction. So you can see that the lowest point on this right here is at 0, right? I'm just looking at the y values on this one, not my x's. So if this is the point -4, 0, right, I'm just looking at the y value, not the x for range. So this graph starts at 0, and according to this, it's going to continue getting higher and higher and higher forever. So the range on this guy, we would say, goes from 0 towards infinity. So that would be our range. As far as this one goes, you can see that this graph, based on this curve and this curve, remember, you're not looking at the vertical line. This is an asymptote, right? This is like an imaginary boundary line that limited our graph from left to right. But what we're looking at is, here's the portion of the graph going up and down. So I got that curve and I have that curve. You can see that it goes up forever and it goes down forever, except for this piece right here in the middle at 0, right? It does not hit the x-axis, right? And so it never hits 0. So this guy goes from -infinity up to 0, but it does not include 0. So we're going to union that with 0 to +infinity, and now we have covered everything except 0 with that statement right there. So there's our range. And then this guy, last one, you can see this guy, lowest point is 0, goes up forever. If it was just the general function like we already talked about, I would have said that it goes from 0 to infinity, inclusive, right? That would have been this entire graph, but according to it representing side lengths of a square and area, right? Just like my side lengths cannot be 0, my area cannot be 0, or it would not exist. So again, we are not including 0 in this. So really the range in this case should say 0 to infinity, non-inclusive, right? And this would have been the appropriate range for representing an area. So something else I want to introduce to you. One of the things that we're going to discuss as the year goes on is, remember, a lot of this is preparation for calculus. And so there are some things in your textbook that sort of some extra examples and things, ideas. They're going to have this little sigma symbol next to it, that Greek letter sigma. These represent your link to calculus, right, with the concepts that we're doing. And so always good, especially for those going on to calculus after this year. Take a look at that kind of information. I throw it in as much as I can, but we're not going to be able to cover every little thing in the book. So I always encourage you to look at those concepts sort of on your own as well. You can always ask me questions about it. That would be fine. So let me just discuss something really quick on page 82 and 83, and I'll throw these in as well as far as the increasing and decreasing ideas on page 84. So let me jump over to that. Give me one sec. As we approach the end of the year and we get into our 2 chapters of calculus that I'm planning on covering, one of the first things that we talk about that you're introduced at the very beginning of any calculus course is the idea of limits and continuity. And so these guys right here, continuity just has to do with a graph being continuous, right? And so as you were to look at this graph right here, this graph, pretend there's arrows at the end of these. This graph goes left and right forever, and there's no break in the graph, right? There's no cuts, there's no breaks, there's no asymptotes, there's no holes. So this is a continuous graph everywhere you have x. If you look at this one has a hole in the graph right here, right? And so that little hole in the graph, which we're going to get into later, whenever you see a hole in the graph, we call that removable discontinuity, right? So that has removable discontinuity that you're seeing on here whenever you see a hole in the graph. So it is discontinuous at point A, right? So it's continuous everywhere except point A, so we call that removable discontinuity, or it is discontinuous at point A. Right here, where you see this gap in the graph, obviously not continuous. So this is a different kind of discontinuity, where you not only have a hole in the graph, but there's actually a gap that you see right here. So they call this jump discontinuity. It's like we are moving along this curve, we're moving, and then to get to the other portion of the curve, we have to jump over this gap, and we get to this guy right here, right? And now it's continuous forever to the right after that point. So that is jump discontinuity, and then infinite discontinuity is where you have your asymptotes, right? And so if there's an asymptote in the graph, like you see, there's an imaginary horizontal boundary line that goes right here through the graph, right? This is called infinite discontinuity. So to the left of the vertical asymptote, you can see that our graph is continuous as it approaches A, but it will never actually get to A, right? It's heading towards negative infinity in its range, but it will never hit the x value of A, right? And then on the right side of A, it's approaching positive infinity as it gets closer to A, but will never actually get to A, right? And so this is infinite discontinuity. So a few different types of discontinuity that we're familiar with. If there's no discontinuity, then we just say it's continuous, right? And that's sort of the other side of that. So really want you to start learning some of those ideas. Let me move on to the next page. So a little more information over here that just sort of further explains what we're talking about as you are approaching an x value. So again, these are the three types of discontinuity that we're going to be familiar with. So great page for reference, for future reference, that you can come back to this. You might want to make note of this as we'll be talking more about limits and all those ideas. So let me go one step further here. As far as increasing and decreasing, another introduction to calculus idea as we're looking at graphs. A graph is increasing as the y values are getting bigger and bigger and bigger, right? And so that's the idea of increasing. So this graph is forever increasing. As I go from left to right, it is constantly going up, right? It is getting bigger and bigger and bigger. It doesn't matter if the curve is flattening. As long as the y coordinates get bigger as you move to the right, then it is forever increasing, right? Decreasing obviously is just the opposite of that. Decreasing would be as your y values get smaller as you move to the right. Constant would be where your y values stay the same, right? So if my y value is not changing from left to right, then it is constant. So taking those three ideas, you can put those into one graph. So what you're going to be asked on some future things is, where is the graph increasing, decreasing, or where is it constant, right? And so you can see right here that the graph is decreasing, and they don't use arrows on these, but it would be nice if they did. These graphs do go on forever. So from negative infinity all the way up to -2, my graph is decreasing. By the way, they do, unless there's a hole in the graph, they do use an inclusive symbol whenever we're talking about increasing and decreasing. So it was decreasing all the way up to -2, and then you can see from -2 to +2, it's constant. And then from +2 to infinity, it is increasing as it goes up, right? And so here's kind of all of that put together for how we would identify those things. So great examples for you to take note of right there. One last idea, hang with me. I know this is kind of a long one, kind of a lot to squeeze into this first section here. That's why I'm breaking this up over 2 days. This is actually only part 1, so last page. Wanted you to see this guy. So here's some examples for increasing and decreasing. For a lot of these things, we will take a graphical approach, meaning we're just going to be determining our answer based on looking at the graph. For some things, there's still an algebraic approach, and we're going to get to some of those things later. Let me show you real quick on the graphing calculator what you could do here. So if you're using one of these, you can go to your y equals. Let me clear out the old one. I'm just going to type in the graph there. So here's right here is our button for x. So I'm going to type in x minus 2, close parentheses, squared. So I'm just going to type it in so I can take a look at it. Although this one, I don't know that you would need a calculator. You could probably come up with this graph on your own just by shifting your parabola to the right 2 units. But anyway, there's going to be some that are more complex. So as I put that in, I'm going to go ahead and hit graph. So here's the same one that they're looking at. So as far as increasing and decreasing are concerned, you can see that from negative infinity, I'll kind of move this way, from negative infinity all the way up to positive 2, my graph was decreasing. And then from 2 to positive infinity, my graph is increasing, right? And so here's the way that we would write that graph. So here's the decreasing, here's the increasing that we can tell by looking at the graph. So same thing with something like this. This is not something that would be very easy to do without looking at the graph. So want to make sure we'd be able to graph this one as well. So again, I would type it in just the way that you see it there. I'm going to go back to my y equals. Let me clear out the old one. I'm going to type this in. Super careful with how you type in fractions. If you just typed it in as x squared divided by x squared minus 4, you will not get the correct graph. And the reason for that is your calculator does not know that that minus 4 is on bottom unless you tell it it's on bottom. So there's 2 ways to do that. One way would be to put your denominator in parentheses. So after your division symbol, if you would have said parentheses x squared minus 4, now it knows that all that stuff, let me get rid of this. Now it knows that the minus 4 is on bottom because of the parentheses. So that's one way to do it. The other way to do it is kind of a cool feature in here under the F1. You'll notice it's in green, so I'm going to hit the green button first. I'm going to say alpha F1. It pulls up this little menu. That first option is a fraction mode. So if I hit enter, now it sets up the fraction for me. Now I don't have to worry about the parentheses. I'm just going to type in x squared on top. I'm going to type in x squared minus 4 on bottom. Oops. There we go, minus 4. And now I don't have to worry about the parentheses. My calculator knows what's on bottom and what's on top. I go ahead and hit graph. And the graph that is slowly coming up for you represents that one right there. So you can see on this one that this graph is increasing from negative infinity all the way to negative 2. So here's my vertical asymptote at negative 2, and you can see where that would have come from. Right? I know that x squared minus 4 cannot equal 0 because it's on bottom of a fraction. If I solve that inequality, or sorry, solve that equation, I square root both sides. X cannot equal plus or minus 2. So that's why I get the vertical asymptotes at positive and negative 2. Right? And so that's why on this graph I have my vertical asymptote at negative 2, vertical asymptote at positive 2. So we are increasing from negative infinity to negative 2. We are increasing from negative 2 to 0. We are decreasing from 0 to negative 2, or sorry, positive 2, and we are decreasing again from positive 2 to infinity as we look at those guys. So one thing I wanted you to notice on this one is because this graph is discontinuous, it has an infinite discontinuity. It does not ever hit -2 or +2. So this is a case now where it is non-inclusive when you write those answers, right? Because it's a discontinuous graph. So now they're using a non-inclusive symbol because the graph never hits those points on the graph, right? So really important that we notice that. So that's pretty much it. If you want one extra practice here, I'm going to show you one more just for practice. If you're good to go, you can move on. If you want to see one more, here you go. So here's a case where I would definitely use my graphing calculator. Just going to type in the function the way that I see it on my page. So x cubed divided by 3 minus x squared plus 1. So it should look like this. I didn't need the whole parentheses and fraction bar like I showed earlier because only the 3 is on bottom of my fraction. There is nothing else other than that one term, so there's not going to be an issue. I'm going to hit graph. Here we go. So you can see on this one, this is a continuous graph. There are no breaks in it, so when I write my increasing and decreasing intervals, I am going to use the inclusive symbol for this. So you can see that this is increasing from -infinity all the way to where x is 0. And then it is decreasing from 0 to that guy right there, which is at +2. And then it's increasing again from +2 to infinity. So I'd be writing all of that with inclusive symbols as far as stating increasing and decreasing intervals. Real quick, I'll end with this. What if I'm not sure where that is? Right? What if I'm not sure if that's at +2 or maybe it's like a decimal or a fraction that's really close to 2, but I'm not sure. So you can actually do that in your calculator. It's right here under calc. So I'm going to hit second calc, and I can see that that little lower portion of the curve was a minimum value. So hit enter. I'm going to do my left boundary, which is to the left of that minimum, hit enter. My right boundary is to the right of that minimum, and hit enter. When it says guess, I hit enter, and sure enough, you can see my minimum was at 2, right? And so I was correct on seeing what I thought I was seeing on the graph. Sometimes they come really, really close to that point. We have to sort of understand the limitations of our calculator sometimes, and it is a value of 2. We can tell right there. So anyway, that's it for part 1 of 1.2. See you next time.